computation that can be carried out by mechanical means can be performed by some Turing machine. So Turing thesis says that if there is any computation that can be mechanically performed, then that computation can also be performed by some Turing machine. So from this you can understand how powerful a Turing machine actually is. So we have discussed about other machines in this course of lecture series, like finite state machines and push-on automatas, and we saw that how limited they are and what are the limitations that they had. But seeing this Turing thesis, you can understand how much more powerful a Turing machine is as compared to finite state machines and push-down automata. Now, this is the Turing thesis that we have, and there are few arguments for accepting this thesis. Now let us see what are the arguments that are used to accept or support this Turing's thesis. Number one, anything that can be done on existing digital computer can also be done by a Turing machine. So any computation that we can do on an existing digital computers that we have today, that can also be done by a Turing machine. So we see how powerful Turing machine is. And then number two, no one has yet been able to suggest a problem solvable by what we consider an algorithm for which a Turing machine program cannot be written. So this means that if there is a problem that you have, and if you are able to write an algorithm for solving that problem, then you will also be able to design a Turing machine program which can be used to solve a same problem. So till now nobody has been able to suggest any such kind of problem whose algorithm can be written but cannot be solved by a Turing machine. That means if you are having the algorithm, if you are able to design the algorithm for a problem or for solving a problem, then that can also be solved by a Turing machine. So that again shows how powerful a Turing machine is, and these two arguments, they support our Turing thesis, which says that any computation that can be carried out by mechanical means can be performed by some Turing machine. So that is about the Turing thesis. Now let us see what are the languages that can be accepted by a Turing machine. So the languages that can be accepted by a Turing machine, it is known as recursively enumerable languages. I have discussed this even during the introduction, and it says that a language L and a set of input symbols sigma is said to be recursively enumerable if there exists a Turing machine that accepts it. So if a language is acceptable by a Turing machine, then that language is said to be a recursively enumerable language. So we know that we have discussed other machines like finite state machines which accepts regular languages, and then we discussed about push-on automata which accepts context-free languages, and then Turing machine, it accepts recursively enumerable languages. Now when we talk about these languages, there are some other classes of languages that we need to discuss, like Turing recognizable languages, Turing decidable languages, and also languages that cannot be recognized or decided by Turing machines. So those things we will do a separate lecture for that, and when you understand what is Turing machine and what are the classes of languages accepted by Turing machines, those classes of languages later on will be very easy for you to understand. So first of all, we will try to understand how Turing machine works and what are the kind of languages that is accepted by the Turing machine. So in this lecture, we have studied about the formal definition of Turing machines, and we also saw the Turing thesis, and we also saw the languages accepted by Turing machine, which is the recursively enumerable languages. So from the next lecture, we will be taking examples of Turing machine where we will see how Turing machines are designed and how they actually work. So thank you for watching this, and see you in the next examples of Turing machine where we will see. In the previous lecture, we have seen the formal definition of Turing machine, and in this lecture, we will be seeing an example of Turing machine, and we will see how we can design a Turing machine for a given language. Alright, so here we have a question which says, design a Turing machine which recognizes the language L equal to 0 1 star 0. Now what does this language mean? This language means it should have 1 0 followed by any number of ones followed by 1 0 at the end. So if you see that this language is a regular language, we might have taken this example even in our previous lectures, and you must be knowing that this is a regular language, and we actually can design this language using a finite state machine because this is a regular language. But we are going to do it using Turing machine so that we can understand step by step from the very simplest example of how to design a Turing machine. We don't actually need the full power of Turing machine in order to design this language. This can also be done using a finite state machine or a push-on automata. But we are going to design it using a Turing machine to show you how it actually works from the very basic or from the very simplest steps. Alright, so let's see how the Turing machine for this can be designed. So here we have the Turing machine for the language that we have to design, which is L equal to 0 1 star 0. So here we have the starting state, which is A, and then we have two states B and C, and then we have two final states, which are the reject state and the accept state. And let us see how it works. So as we want to accept 0 1 star 0, in the initial state or the starting state, when we get a 0, we go to the next state B, and then in our tape we write the symbol X and we move right on our tape, and we come to state B, and we know that we have to accept any number of ones after we accepted this 0. So in state B, if you get any number of ones, you always stay in state B, and then in our tape you write the symbol Y, and then you move right on the tape. And after getting any number of ones, finally we need to get a 0. So if you get a 0, what you do, you proceed to the next state, which is state C, and then you write X on the tape, and then you move right on the tape. And after we reach the state C, we see that there is nothing more to take. So what we do, we read the blank symbol. That means we read something that is empty or the blank. And if we see the blank symbol, what we do, we don't write any other symbol other than the blank symbol into the tape, and then we move right on the tape and it goes to the accept state. So this is how it works. So let us just take an example and see how this works using the tape. So let's say that we are going to take this string 0 1 1 0. So we say that there is 0, and then we are allowed to take any number of ones. So we have two ones here and we have a 0 at the end. So this should be accepted by this Turing machine. So first of all, we come to the tape, and my tape head is over here in the beginning. And then if you get 0, what happens? We write X on our tape. So in my tape, let me write X, and then you go to state B and you move right on the tape. That means my tape head comes over here now. Alright. And now the next input, we have already read 0, and the next input that we have is 1. Now if we get 1, what happens? We are in state B, and in state B if we get 1, we stay in B itself and we write Y onto our tape. So this is my tape head. So here I write Y, and then what we do, we move right on the tape. So my tape head, which was here, will now move to the right, which is one step right. Alright. And then the next input that we have is another 1. So we are still in state B, and if you get another 1, what you do, you stay in state B and you write Y on the tape, and then you move right. So my tape head is over here, I write Y over here, and then my tape head will move one step to the right, which is over here. Okay. And then the next input that I have is a 0. So in B, if you get a 0, what happens? It goes to state C, and then we write X on our tape and we move one step right. So I will write X on my tape head is over here, so just below that I write X, and then we have to move one step right, this right over here. So I move one step right, and now we see that we have reached the end of the string. So here there is nothing, and we consider this to be the blank symbol. So we are in state C, and when we read the blank symbol, what happens? We write blank on the tape, and we move one step to the right and we go to the accept state. So here is my tape head. I will write the blank symbol and I will move my tape head one step to the right. Okay, so this is the condition of my tape now, and then I have reached the accept state. So since we have reached the accept state, this string will be accepted. So this is how the strings will be accepted or recognized by the Turing machine. Now, there is one question that you can ask: why are we writing these symbols X, Y, Y, X on the tape? So as I told you in the beginning, this is a very simple language. It is a regular language, and you actually do not need the full power of a Turing machine in order to implement this. But we have to do this because we are using the Turing machine, and particularly for this language, these tape symbols don't have any particular use. They are not of any particular use for accepting this language, but we are just doing this in order to show you how Turing machine works and how the tape actually works. So you don't actually need the tape, but we have to.
Shakti Salgaonkar has been absent from classes all day.
In the previous lecture, we have seen the formal definition of Turing machine, and in this lecture, we will be seeing an example with the blank symbol. So we are in state C, and when we read the blank symbol, what happens? We write blank on the tape and we move one step to the right and we go to the accept state. So here is my tape head. I will write the blank symbol and I will move my tape head one step to the right. Okay, so this is the condition of my tape now, and then I have reached the accept state. So since we have reached the accept state, this string will be accepted. So this is how the strings will be accepted or recognized by the Turing machine. Now, there is one question that you can ask: why are we writing these symbols X, Y, Y, X on the tape? So as I told you in the beginning, this is a very simple language. It is a regular language, and you actually do not need the full power of a Turing machine in order to implement this. But we have to do this because we are using the Turing machine, and particularly for this language, these tape symbols don't have any particular use. They are not of any particular use for accepting this language, but we are just doing this in order to show you how Turing machine works and how the tape actually works. So you don't actually need the tape, but we have to use the tape because it is a Turing machine. And another thing that you need to know is that in the first lecture itself, I told you that Turing machines, they are deterministic. So deterministic means what? When you draw the transition diagram, there should be a transition for each and every input symbol that we have for each and every state. So let's see if this is deterministic or not. Here we have state A, and then in this language, the input symbols that we have, they are 0 and 1. And the special symbol that we have, which is the blank symbol, that is this one. So we need to have transition for the symbols 0 and 1, which is the input symbols, and we should also have transition for the blank symbol. So remember that blank is not an input symbol, but it is a special symbol, and we need to have transition even for this. So in state A, we see that on 0 it goes to B, and on 1 it goes to reject, and on the blank also it goes to reject. So for all the three, it is having transitions. And even in B, in 0 it goes to C, in 1 it goes to B itself, and on the blank it goes to the reject state. So even in C, we see that for both 0 and 1 it goes to the reject state, and on blank it goes to the accept state. So we see that for each and every symbols, input symbols, including the blank symbol, there is a transition for all the states that we have. And we see how this Turing machine was working. That is, for 0 followed by any number of 1s followed by 0, it comes to the accept state. So in all other cases, like if you are getting 1 in the beginning or blank in the beginning, it goes to the reject. And after getting a 0 in the beginning, if you are getting a blank, then it is going to the reject state. And also in C, after getting this 0, which is this final 0 over here, and after this, instead of getting a blank, if you are going to get 1 or 0, it will also go to the reject state. So this is how this Turing machine works. And another thing you need to remember about the Turing machine is that Sometimes when we draw the Turing machine, you may notice that some edges may be missing. So if some edges may be missing, then you should understand that that edge by default it leads to the reject state. So when we draw this Turing machine in some examples that I take, if you don't see an edge or if you don't see a transition for a particular input, don't think that it is wrong, because I already told you it is deterministic. And thinking that it is deterministic, and if you are not seeing an edge, you may sometimes think that it is wrong. So don't think it is wrong, but just know that if an edge is missing, it goes to the reject state by default. So here we have transition for all inputs on all the states, and we have two final states, which is the accept state and the reject state. And unlike finite state machines, where in the final state also we need to have transition for the inputs if it is a deterministic finite automata, but in this one we don't give transition for the accept state and reject state. They are two states that are either used for accepting or rejecting. So it is deterministic, and we saw how the tape is working, and we also saw the important things that you should remember about the Turing machine. So this was just a simple example to help you understand. So from the next lecture onwards, we will be taking more examples where we will be discussing more complicated languages that cannot be designed. In this lecture, we will be seeing another example of Turing machine where we will see how to design a Turing machine for a given language. So our task is design a Turing machine which recognizes the language L equal to 0 power n 1 power n. That means we have to design a Turing machine which accepts this kind of language where the number of zeros should be exactly equal to the number of ones that follows. That means if you have n number of zeros, then you should exactly have n number of ones that follows those zeros. And if you remember, we have talked about this example even in our previous lectures when we discussed about finite state machines, and we saw that we could not design this using finite state machines. Why? Because we need to keep a count of how many zeros are there in order to repeat the exact same number of ones so that we can achieve this language. But we saw that finite state machines, due to their limited memory and due to their limited capability, it was not possible to design this language using a finite state machine, and hence we said that this is not a regular language. This particular language is not a regular language. So we shall see in this example, using a Turing machine, how can we design this language. So first of all, I will explain to you the algorithm of how this can be done. We will design an algorithm which will be able to accomplish this task of accepting this kind of strings, and then from this algorithm we will see how we can design the equivalent Turing machine for it. Alright, so here we have the tape sequence which is there in our Turing machine, and then the algorithm, it says that the first step says change 0 to x. We are going to replace the first 0 in our tape to x, and then we will move right until we find the first one, and if you cannot find the first one, you have to reject. That means the string will not be accepted. And if you are able to find a 1, you have to change that 1 to y. And after you do that, you have to move left until you find the leftmost 0 in the tape. And this process will be repeated until no more zeros are there. And you have to make sure no more ones remain as well. Alright, so don't get confused by seeing this algorithm. I will explain it to you using this tape. So let's say that we have our tape over here, and then there is an input in this tape 0 0 0 0 1 1 1 1. So we see that we have 4 number of zeros followed by 4 number of ones. So the number of zeros and ones are equal, and hence this string should be accepted by the Turing machine that we are going to design. So let's see how this algorithm works. So it says change the first 0 to x. So first of all, I have my tape head over here, and then I see that there is a 0 over here. This is my first 0. So this 0, I replace it with an X. This is what step 1 says. Then you have to move right to the first one. So I have to move my tape head right until I find the first one. So I have to move
So when I came to US, I was
during machine. Task should be
भाई तो
there is
टाइम है
an
इसका
input in this tape 00001111. So we see that we have 4 number of zeros followed by 4 number of ones. So the number of zeros and ones are equal, and hence this string should be accepted by the Turing machine that we are going to design. So let's see how this algorithm works. So it says change the first 0 to X. So first of all, I have my tape head over here, and then I see that there is a 0 over here. This is my first 0. So this 0, I replace it with an X. This is what step 1 says. Then you have to move right to the first one. So I have to move my tape head right until I find the first one. So I have to move step by step to the right. One step to the right, one step to the right, one step to the right. And when I take the next step to the right, here I find my first one. So when we find the first one, what you have to do? You have to change that 1 to Y. So I will change this 1 to Y. Okay. And then what we have to do, you have to move left to the leftmost 0. So I am over here right now, and I will keep moving left until I find the leftmost 0. So let me move left step by step, one step to the left, one step to the left, one step to the left, and here I find that this is the leftmost 0, because here I don't have 0 anymore, it is an X. So here I find the leftmost 0. And what does it say? It says repeat the above steps until no more zeros are to be found. So I have to do the steps that I just did. So when I find the 0, I just replace it with X, and then again I have to move right to the first one. So I move right like this, and here I see that this is not a 1 anymore, this is a Y. So which is the first one now? It is this one. So I will replace this with Y. Now I have to again move left, searching for the leftmost 0. So as I move left, this is the leftmost 0. I replace it with X, and then I move to the right to the first one. Now which is the first one? This is the first one now. I replace it with Y, and then I move left again, searching for the leftmost 0, which is this one, and I replace it with X, and then I move to the right, searching for the first one, which is this one, and I replace it with Y. Now if I look, there are no more zeros present, and also all the ones are consumed. So our tapes looks like X X X X Y Y Y Y, and the next symbol is a blank symbol. So this string will be accepted. When you are doing this, like suppose you find a 0, and when you go searching for the 1, if you don't find a 1, then you will reject. That means the number of zeros is not equal to the number of ones. So in that way, you can find if the number of zeros and number of ones are the same. So this is the algorithm that we need to follow. Now let us see how we can design the Turing machine for this using the transition diagram of the Turing machine. So here I have the Turing machine, which is going to perform exactly the same task that was written in our algorithm that we just saw before. Now let's see. Here we have the starting state, which is A, and then we have states B, C, and D, and we have the accept state. Now if you see, there is no reject state that is mentioned over here, and it doesn't mean that there is no reject state. It means that whenever there is a missing edge for any transition, that will implicitly go to the reject state. So it is just that we have not specified it separately, but there is a reject state. And where is a reject state? Any edge that has a missing transition, that will go to the reject state. Alright, we already said that Turing machines, they are deterministic. The ones we are designing, they are deterministic. So in determinism, what is it? You need to have a transition for every input, for every state. And in Turing machine, you also have to consider the blank symbol. So if you see that in state A, it has transition for 0, it has transition for y, and it has transition for the blank. But we see that it is not having transition for 1, the symbol 1. So if you get a 1 in state A, that means it goes to the reject state. And that is true because in the kind of language that we are going to design, we want zeros followed by ones, not ones before zeros. Okay, so that was just an information. Now let's see how this works. So we are in the starting state, and in the starting state, we get the first 0. So when you get the first 0, what you do, you replace it with x and you move right. So here is my tape head. I replace this 0 with x and I move to the right. And now I am in state B. And in state B, what happens is that, what is the next step as I told you? From here, you have to go to the right searching for the first one. So you have to reach till here, and state B will help you do that. So in state B, what happens? Whether you encounter a 0 or y, whatever it is, we are not going to replace them with anything different, but we are going to write the same thing. So that basically means that you are not replacing anything. All right. And then you just keep moving right. So if you are getting zeros, replace it with 0 itself and move right. So 0, 0, 0. And then here I encounter my first one. So when I encounter my first one, what happens? I have to replace that one with a y, and then I have to move left. So I have to replace this with y, and then I have to move left. So my tape head was here, so it will come over here now. And then in state C, this state C will help you to go back until you find the leftmost 0. So in the algorithm, I already showed you, after you reach here, you have to move left until you find the leftmost 0. So the state C will take you left without replacing anything different. That means if you see a 0, you write a 0. If you see a y, you write a y. So basically it means you are not replacing anything and you just keep moving left. So I keep moving left like this, and till when do I move left? Till I encounter an x. So I move from here to here, and I come here, and when I reach here, I encounter an x. This is not 0 anymore, this is an x. Now when you encounter an x, you understand that following that you will have the leftmost 0. So what happens when you reach this x, you move one step to the right. So after reaching this, I move here and my tape head is over here right now. And then what happens? You come to state A, and then in state A, if you see 0 again, this whole process will continue. And yes, I am seeing a 0, so the whole process has to continue. So this will be replaced with x, and then we move right, and this will be replaced with
Why?
y, and then again we move left, replacing this with x, and then we move right, replacing this one with y, and then we move left, replacing this.
चलो तब तक इसको draw करते हैं. I love to sketch these things. Sketch the machines. Make a straight line. Make a circle. The right A. Automatically end up writing. Not automatically. You end up writing straight. If you keep the knot to the left. Thing is that